My name is Jenny Plant. If I'm feeling fancy, it's Genevieve Plant, but most people call me Jenny. But yeah, as Julia mentioned, I'll be talking about our work investigating methane emissions from flaring in the United States. And as Julia also mentioned, this is part of the fuel project. So I'll just give some kind of quick overview of that as well. So it's a collaborative work. There's those of us at the University of Michigan, and Julia and Adam there at Stanford, as well as colleagues at the Environmental Defense Fund and Scientific Aviation. And then funding for the project is from the Alfred P. Sloan Foundation. Let's see. Great. Yeah, so the fuel project, as Julia mentioned, with the superscript 3, stands for Flaring and Fossil Fuels, Uncovering Emissions and Losses. So it aims to sample and create new observational data sets for two traditionally undersampled parts of the oil and gas sector, namely flaring in oil and gas regions and offshore infrastructure. So, you know, this whole call is probably people measuring methane in different aspects, and particularly in oil and gas. But historically, these two sectors and these sources haven't been, in terms of observations, hasn't been isolated or studied nearly as much as, you know, things at the basin scale or other sources in these domains. So the fuel project is based on new observations, so new measurements in offshore regions as well as onshore flaring areas. So over the course of 3 years, we conducted airborne campaigns with our colleagues at Scientific Aviation. So in 2020, we started, just to kind of give you a quick overview of the project, we started in 2020 in the Gulf of Mexico, looking at infrastructure offshore, then moved onshore to look at flaring in the Eagle Ford and the Permian. In 2021, we started onshore in the Bakken in North Dakota, and then moved to Alaska in the North Slope and Cook Inlet, looking at offshore infrastructure there, and then ended the 2021 airborne campaign off the coast of California. Then in 2022, the aircraft went back to the Gulf of Mexico to finish off our airborne sampling there. And then to complement the airborne data set, actually Julia and another teammate, Alan, conducted ground surveys in the Bakken, one in 2021 and another in 2022. So I won't be talking about the offshore part of the fuel project, but if you're interested in that, please reach out. But you can also check out our website. They're listed at the top for the fuel project. And also there, a publication should be coming out fairly soon about some of this data in the Gulf of Mexico. So I would be on the lookout for that as well. But as the talk title suggests, I'll be talking about flaring today. And with this group, you know, I don't think I really need to say what flares are. Probably some people on this call could teach me much more about flares than I could teach them. But I'll just say that this is flaring of gases associated with the oil extraction of oil. So this gas is disposed of using the controlled combustion of a flare, and it can be done for a number of reasons. It could be safety concerns or emergency situations, as well as regulatory purposes, or if there's not enough economic incentive or regulatory incentive to do something else with the gas. So if we want to look at flaring kind of from a very broad perspective in the US, a good place to start is with the VIIRS data set. So that's a space-based data product, the visible infrared imaging radiometer suite, instruments on board the joint NOAA-NASA satellites, in particular the Nightfire data product from the Earth Observation Group. So that uses nighttime measurements across the globe from these satellites, looks at various spectral windows to extract heat anomalies from which they can identify flaring locations, as well as heat from the flare, and also infer the volume of gas being flared. So if we shown here in the red dots are VIIRS flaring locations, I believe, for the 2020 annual product. So you can see flares across the US, but your eyes are probably drawn to some clusters of flaring, like high flaring regions in North Dakota and then around Texas. So I'll get more into that in a bit, because that's where we ended up sampling. But if we kind of stay at this national level, if we sum up all the gas being flared, that's the time series on the left plot there at the top in black. So from 2012 to 2020, you can see some fluctuation and variability in the amount of flared volumes in the US. And if you're trying to think about what's driving these trends, you can look to similar trends in the natural gas gross withdrawals, as well as production of crude oil. So that just gives you a sense of what is driving these flares or these flaring volumes and what causes the total national level amount of flare volumes to fluctuate. So I guess I motivated the fuel project by saying that, part of it's to look at flaring, which is an undersampled part of the oil and gas sector. But that's not to say flaring itself has never been studied or examined. So in the United States, the EPA commissioned several studies in the 1980s to characterize flares, particularly industrial flares, and to look at their efficiencies and performances. And a lot of the assumptions and emission factors that we use today are from these studies. So since the 1980s, there's been additional examinations of larger scale flares. They tend to be at industrial scale sites, so things like refineries and chemical plants. And they're summarized here in this table from the EPA document entitled Parameters for Properly Designed and Operated Flares. So something I'll just draw your eye to is the test methodology in that rightmost column. So it's listed as extractive or some form of FTIR, meaning Fourier transform infrared spectrometry. So these are methods, definitely an extractive method, but to some extent FTIR methods, despite it being remote, require, you have to be somewhat close to the flaring infrastructure itself, which then leads you likely need, people on the ground to let you nearby to sample the flare. So in addition to sampling of these kind of large scale flares, there's been a number of works looking at the theory and lab performance of flares, and investigating things like how their performance varies and the relationship between things like combustion efficiency and operational parameters and conditions. So this is not an exhaustive list, and if you study flares in your paper isn't on here, I'm sorry, but it's just to give you a sense of kind of what's been the focus of a lot of flaring studies in terms of their performance. So if you think back to that map of Veer's flaring locations, there's a lot of flares in the US. It's one of the top countries in the world in terms of not only flare volumes, but also flaring infrastructure. So there's a real sampling challenge there. If you need ground access, like some of these methods require, it's not necessarily an efficient sampling design to do that from the ground. So there haven't been many measurements of real world flares because of the difficulty of sampling a large number of flares in a somewhat efficient manner. So in theory, an airborne type platform would solve a lot of these problems, right? You wouldn't need access to the ground, and you could cover a relatively large geographical area in a fairly time efficient manner. So there's been a handful of studies that have shown that you can measure and sample flares from the air. They're mostly done in the Bakken in North Dakota, and they sampled, from 10 to 37 flares. And as I'm looking at this, I'm realizing I'm forgetting a very recent paper that just came out looking, Jacob Shaw et al. And it just came out looking at flares offshore in the North Sea. I believe they looked at something like 60 or just about 60 flare plumes. So again, it's something in the kind of tens of flares, but there's a lot of flares in the US. So the question still remains is, are these existing studies representative of flaring at something like the basin or the national scale? That's what we aim to do as part of the fuel project. And so we needed to go to the places where most of the flaring is happening in the US. So for the US, those are the regions of the Bakken in North Dakota, the Permian in New Mexico and in Texas, and the Eagle Ford also in Texas. So those shown here superimposed on this Veer's flaring map as those colored boxes. And then you can see the dates that we sampled them. So in 2020, we were in the Permian and the Eagle Ford. In 2021, we were in the Bakken. So just kind of looking at these clusters of flares, you can already see these boxes encompass a good amount of the flares at the national level. But just to kind of drive that point home, if we sum up all the flare volumes in those boundaries for those various domains, we get these, hopefully you can see my cursor, we get these bar plot time series from 2012 in the darkest color to 2020 in the yellow color. And that's for the Bakken, the Eagleford, and the Permian. Now, if we combine all those regions together into the regions we're sampling as part of the fuel project, we get this series of bars here, which when we compare it to the national total, you can see they look very similar. So not only is the magnitude very similar with these fuel regions or these high flaring regions being responsible for upwards of 80% of the total flare volumes in the US, but you can also see their temporal variability drives the temporal variability of national trends. This is really where most of the gas in the US is being flared. So to sample it, these regions, we had 12 dedicated airborne sampling flights. Well, I guess 12.5, we had one partial flight as well. And each flight was around 4 to 5 hours in length and specifically targeted flare sites on the ground. So I'll talk about that more in a second. Additionally, I'll show here data from one of the ground surveys in the Bakken. And that surveyed 601 active flares over an 11-day period. And I'll show a bit more about that too. So to execute our airborne sampling of flares, we worked with our collaborators at Scientific Aviation in their payload system. So this is the Mooney aircraft. It's a small aircraft. There's there's inlets under the wing shown here in this inset. They're bent and they're facing away from the direction of the motion of the aircraft, such that the sampling is done through the pumps on board the aircraft, and that air is pulled into the instruments rather than being, injected in by the motion of the aircraft. So we have a Picaro on board to give us carbon dioxide, methane, and water vapor. Not shown in the picture, but flown on the fuel flights were an EcoFig 6 and a Teledyne instruments to give us NO and NO2 combined to give us NOx. There's other meteorological measurements on board, and also Scientific Aviation's differential GPS antennas to extract wind direction and speed. So the strategy here would be the flight team, which would consist of a pilot and a flight scientist in this little aircraft, would start the day with a preliminary set of flare locations where the team had identified flares either from VIIRS or other sources that we expected to be there. They were also tasked with, while they were in the air, if they saw other flares that they believed they could sample from an aviation perspective, to do that as well. So we had this combination of targeted and opportunistic flaring. So the team would go out, they fly quite low. So you can see the flaring infrastructure from the air. So I'll play this video, hopefully it actually plays. Sorry, I didn't realize I had audio. But yeah, so you can see the flight team coming in, identifying the flare structure from the air, and the pilots in particular said that they would use the flaring infrastructure and even the flame, if it was bent, to give them a sense of how they needed to adjust the altitude, such that when they came downwind, that they would be likely intercepting that combustion plume coming off the flare. And I also like the video because it shows you how bouncy it is to fly in the aircraft. So this is another kind of animation of what that looks like, but from the top. So here's one, it's a different flare location, but here they come in and they hit the combustion plume on the first try, and then they loop multiple times downwind to get multiple intercepts of that flare combustion plume. So the corresponding time series is shown here on the right. So for CO2 and methane, and you can see these spikes in the time series. So those are these colored regions here where the aircraft is transecting through the flare combustion plume. So to identify or attribute these time signals to flares on the ground, we do a number of things. Well, one, we only look at the CO2 time series because we're looking for the combustion from the flare. And we do that so that we don't confuse it with other potential methane sources on the ground. So we're looking at the relationship between methane and CO2. So we require that the CO2 signature be there, that such that there is evidence for combustion. We only consider it if it's relatively narrow, meaning that it's within, I believe our threshold is 10 seconds, but meaning it's from a nearby source. And then we have thresholds for an amplitude has to surpass such that it overcomes the variability seen in this regional space. So then for each intercept, so for each corresponding peak of methane and CO2, we look at the relationship between those relative enhancements to tell us how well the flare is destroying methane in the gas. So just to give you a sense of the size of our data set, we, across the 3 regions, intercepted about 670 flare combustion plumes. And we did the most in the Bakken, but then otherwise over 100 in both the Eagle Ford and the Permian. So those are intercepts. Sometimes we intercepted flares multiple times, but other times we only intercepted flares once. So we estimate that we sampled over 300 unique flares over the course of the campaign. So I won't be showing it here, but I mentioned that we had instrumentation to measure NOx on board. So that's still a work in progress, and it will be released in a forthcoming paper. But here the real focus is on methane. So because we're looking to quantify methane, in particular from flares, we're doing a calculation of the methane destruction removal efficiency. So if the combustion of the flare was perfect, it would be destroying all the methane in the flare gas, and that would be 100% destruction removal efficiency. So the default assumption used in inventory and accounting purposes of methane from flares typically assumes that it's 98% efficient at destroying methane. So that's a DRE value of 98, meaning that 2% of methane is released to the atmosphere. So in this equation, we have our observations, which are the mu methane and mu CO2. So those are our enhancements as we intercepted the combustion plume. We also know that the gas is not entirely methane that's being flared. So we account for that with this X gas parameter, which is the molar carbon content of the gas that's attributable to methane. So we don't have information necessarily at the flare stack level in terms of fuel composition. So we have to make assumptions about what the fuel, how much methane is in fact in the fuel itself that's being flared. So to do that, we're pulling average values from at the basin scale from the greenhouse gas reporting program. So for the Eagle Ford, that comes out to 76% methane in the gas, in the Permian at 67% methane, and in the Bakken it's the lowest at 55% methane. So there is an assumption about gas composition. I will say that when we look at something like the basin scale, the calculation isn't that sensitive to this assumption because we're sampling a large number of flares. So some, we're using an average gas composition. So some might be higher for some and some might be lower. So looking at kind of this aggregate scale, looking at population level statistics, it's not widely sensitive to what we assume the gas composition to be. But for each intercept, so each time the aircraft intercepted a flare combustion plume, we can calculate this methane destruction removal efficiency. And that's shown here in these histogram plots for the Bakken at the top, the Eagle Ford in the middle, and the Permian down below. So just to kind of orient yourself, there's this dashed black line that represents that 98% assumption that's used in a lot of inventory and accounting methods. So you can see that, and then there's a log normal and normal fit just to try to guide your eye in terms of what these distributions actually look like. But what you can see is that there's a number of flares that we intercepted with the aircraft that are operating at or around that or above that 98% destruction removal efficiency number. But there's sufficient intercepts where it's operating well below that efficiency target, such that at the basin scale, it's bringing down the average destruction removal efficiency. So this is really what we aimed to extract as part of, or what we aimed to analyze as part of the fuel project. We wanted to understand larger scale trends of flare performance. So these at the basin scale for the regions responsible for the vast majority of flaring in the US gives us a sense of what's happening at the national scale. So that's great. We did what we aimed to do. We aimed to characterize or get representative data at the basin and national scale. But you look at these and you wonder, well, why are some flares operating at much lower efficiencies? And that's what we thought of too. But our sampling strategy was very much designed to extract this type of information, to look at distributions at the population scale. So we didn't design, nor do we have a lot of information about what's going on the ground in any kind of fine scale sense. So nonetheless, we tried to explore possible explanatory variables. I'll be upfront that none of this is going to be satisfactory. So there's really likely going to be a different either sampling or data strategy in terms of how to look at what's really driving performance and what's causing flares to behave the way they do. But to start, a lot of lab-based, or there have been lab-based studies looking at the relationship between things like combustion efficiency and destruction removal efficiency with crosswind speed. So here we're looking at our observed destruction removal efficiencies for the various basins as a function of wind speed at that intercept where we encountered the flare combustion plume. So we don't see anything that's statistically significant in this data. There's a couple caveats here. One is that this is the measured wind speed at the aircraft. So there may be some error when we're attributing that wind speed to the flare stack and the flare base height. So that's something to consider. We also, as I mentioned, we don't have a lot of information about what's going on the ground, but there are some spatially resolved products out there that we can try to compare to, one of which is that VIIRS product. So we went through the exercise of trying to link our observational data set with the VIIRS data set. There's relatively high uncertainty in terms of the geolocation, so the linking of those two spatial data sets. For one, we know we're intercepting a flare plume, but where the flare stack is on the ground is not necessarily evident in our analysis in our current data set. And likewise, in the VIIRS product, there's some error in where the actual flare itself is located. So when we look at the relationship between destruction removal efficiency and temperature, or as well as destruction removal efficiency and volume, we don't see any statistically significant relationships. So we can do something similar with drilling info data. So this is well information. Here I'm showing destruction removal efficiency and well age. But again, there's this kind of issue and uncertainty of linking these two spatial data sets. One, we don't know what well is necessarily connected to what flare, and the aircraft isn't necessarily, or our aircraft data set isn't giving us a great link to where that flare stack is on the ground itself. So yeah, as I said, this is not necessarily the most satisfactory set of plots, but it says that there's not just one parameter out there. So, you shouldn't take away that none of these things are important, like wind speed or temperature, flare size, well age. It just says that one parameter isn't driving the entire trends, such that it breaks through all our uncertainty in how we link these various data sets. But like I said, we were really after the, just to go back, these population level statistics. So But if we're thinking about methane from flares, we can't ignore that some flares are in fact unlit. So the community learned a lot about unlit flares as part of the Permian MAP project. That's an Environmental Defense Fund project. I believe it's the methane analysis project, but please correct me if I'm wrong on that. So they've been doing helicopter surveys to understand emissions and in the Permian from the oil and gas sector. They've done a number of various surveys, but a set of them they published in 2021 found that 5% of the flares were completely unlit in their surveys. They've done subsequent surveys, so I don't think I saw an updated number, but I suspect they might have updates to this as well. But so this is an unlit flare. This is a destruction and removal efficiency of 0, basically. So so this is the Permian. So what, do we know if this is representative of the Bakken or Eagle Ford? Well, to answer that, Yulia, your organizer here, and Alan went out and conducted their own ground survey of the Bakken. So the Bakken, I mean, Yulia can comment on it more, but the Bakken is laid out in such a way that you can see this infrastructure from the roads themselves. So remaining on public roads, they were able to survey the infrastructure within the Bakken. So there are many goals to the surveys, but one was to look at the prevalence of unlit flares. So that I wasn't there, but I believe this is Yulia there operating the infrared camera, looking at a flare. And the surveys sites that they were able to capture over that 11-day period are shown there in the map with the different colors representing different dates. So this is an example of one that they saw, an unlit flare that they saw. So this is with the infrared camera, they can see the methane signature without the heat signature, meaning that the flare is active, it's doing something, it's releasing something, but it's not lit, so it's just releasing methane. So for their 2021 campaign, they surveyed 545 sites, and they found that 601 had active flares stacks, and of those active flares, they found that 3.2% were unlit. So we have a Permian estimate for the prevalence of unlit flares, and here we have a Bakken estimate. So we currently don't have one for the Eagle Ford. So for this work, we're just assuming the average of the Permian, the Bakken, if we have nothing better yet to supplement that with. So now we have estimates of the prevalence, so how many flares at something like the basin scale are altogether unlit, giving us a destruction removal efficiency of 0 for those flares. And we also have our airborne data sets such that we could characterize the performance of active or lit flares. So when we combine those, we are putting it all together in what we're calling an effective destruction removal efficiency. So combining these two kind of categories of how we could find flares performing. So for each of the basins here, just to orient you on this graph, there's a black line all the way to the right. That's 100% destruction removal efficiency, so removal of all the methane in the flare gas. The default assumption of 98% is here. Now these dashed gray lines are mean observed destruction removal efficiencies from the airborne data set. So those are of active flares. So even just looking at those, depending on the basin, we're always below the assumption of 98%. And in the case of the Permian, we're significantly below. But then when we incorporate the prevalence of unlit flares, so this is the influence of inefficient combustion. But when we add in the consideration of the amount of unlit flares from those flare prevalence studies, we arrive at a effective destruction removal efficiency. It varies by basin, but it's considerably lower than that 98% assumption. So as Yulia mentioned at the beginning, this is the subject of our recent paper, but just to kind of like throw you all the conclusions at once from this work and the table there if you're more of a numbers person. So I think of the story as being fairly simple. We thought flares, there's assumption that flares stay lit and that they operate at high efficiency in terms of destroying the methane. There's work pointing to the fact that there's a number of flares that are unlit, both from the Permian map project, but from other projects as well. So we added the component of characterizing the performance, the real world performance of flaring in these high flaring regions in the United States. And when we combine those two together, unlit flares and inefficient combustion from lit flares, we find that the effective destruction removal efficiency is much lower. So across the three basins, the average is around 91%. So that means flares are emitting a lot more methane than we previously thought, if we're assuming that 98% and always lit dual assumption about flare performance. So that means that really anything we do to address flaring in terms of either just reducing flare volumes altogether or addressing reasons that they're malfunctioning, either unlit or inefficiently combusting, would have a much larger, methane benefit and climate impact than we previously thought. So that was the conclusion of our methane story, but that's not necessarily, the end all be all when it comes to flaring studies, in particular with methane. So there's a number of kind of remaining questions that I'll end on, of like things to look at in the future. One, is this representative outside the US? We don't really know. There's that work done offshore, but maybe there's an onshore offshore component, something that needs to be investigated. Is there a temporal variability that we're not capturing here? What is the cause? I think that's the big question we get, is what is the cause of these malfunctioning flares? And are there other sampling strategies that may be better suited to answer some of these questions than what we've shown here? But in the end, I think the encouraging part is that it's something we should theoretically be able to fix. And I think that's an encouraging point. So I'll end there, and hopefully I didn't take too much time, but I'm happy to take any questions or if we talk about anything.